Welcome to online anesthesia video of the week. Today topic is presented by Dr.S.Sivaprasath, working as an assistant professor in Madurai Medical College. He is well known by students as a great teacher. He has undergone liver transplant training in Sir Ganga Ram Hospital in Delhi during 2007 to 2008. He has great excitement and interest in cardiac anesthesia.
Warm greetings from online Anaesthesia and welcome to video of the week, that is advanced mode of ventilation. For the past 3 weeks we have been giving a series of lectures on ventilators. The first one was on physiology of on understanding mechanical ventilation, the second one on basic modes, and third one on scalars and loops. So in continuation I am going to take advanced modes of ventilation. I request the viewers to go and look at the previous 3 episodes for better understanding before going through this presentation. So in this, you can see that there are 3 speedometers. The first one is a very basic car. It just has a speedometer, fuel gauge, and a temperature monitor. The second one has cruise control. That is, you can sit relaxed. Once you are on a straight free road, you can sit relaxed and set a speed and go in that. The third is the ADAS, where your car will control everything, even if the road has bad turns or traffic. So this is how the world is evolving, and the ventilation is also like this. It has evolved a lot. So we should know where you can use these advanced modes and how it will be helpful for you. So in this lecture, I'm going to revise some of the basic modes and how they work. Though you have to look into it, the previous lecture, I'll just go through in a quick sequence, and I'll also teach you what target schemes mean, and I will teach you all the advanced modes as an extension of all the basic modes. See, more than 500 to 600 modes are there clinically now on ventilators. But if you know how to classify them as an extension of a basic mode, it's easy for you to understand and to apply whenever you need it. So ventilation and oxygenation is a complex interplay between CNS, the muscles, the lung mechanics, gas loss and circulation. And derangement in one factor can lead to impairment of the whole process. Probably it can be a mild derangement. You might not be able to appreciate it, but in the long run, definitely ventilation oxygen will be uh, impaired. So mechanical ventilator can improve or support the process by influencing these variables. How does it do? It follows the equation of motion. That is, the pressure generated either by muscle or the ventilator is by creating a flow against resistance and a volume against reluctance. So this is the most basic equation each ventilator will follow. So you don't have anything else, like you can oxygenate a patient with help of an ECMO, but if you are using a ventilator, it will always follow this equation, and by doing so, it will give you safety, comfort, and efficiency. Remember, all the basic modes can do that, but if you want to have a little more, you will need to go for advanced modes. So what are the variables that are going to interplay when you ventilate the patient? So there are 4, that is pressure, volume, time and flow, out of which you can divide equally. Pressure goes to one side and volume, time, flow comes to the other side. In other words, the relationship between volume, time and flow is the flow is the volume integral of time. So whenever you have the variables, pressure is always on one side, volume, time and flow are on the other side. So you will have the broad classification of the modes into pressure-based modes or volume-based modes. So when you come to classify the variables, how they shape the ventilation and how they shape the breath, the parameter that shapes the ventilation is called the control variable. That is the independent variable, which is independent of lung mechanics during the breath delivery. Now again, I have put the equation of motion where pressure is equal to flow against resistance and volume against elastance. So here we have 3 variables: the pressure, the volume, the flow, and 2 parameters, that is resistance and the elastance. If you make pressure an independent variable, the volume will become a dependent variable. If you make volume the independent variable, the pressure will become a dependent variable. So it is always the vice versa in conventional modes of ventilation. So we have got some modes of ventilation like volume control, volume SAME, pressure control, pressure level SAME, and pressure support ventilation. So these are all the parameters which is either volume or pressure, which shapes what type of ventilation you want. Next is how the variables shape the breath. There are three types of phase variables. The first is the trigger variable. The trigger variable is set, and once that variable will shape how the inspiratory valve opens. It could be either time, flow, or pressure. In mandatory breaths, it is always the time that starts the inspiration, and in a patient triggered one, it is always the flow or pressure. Next is how the inspiration ends and goes into exhalation. That's called cycling variable. That also could be time, flow, volume, or pressure. Commonly, time is used in mandatory modes and flow is used in spontaneous modes. Coming to yet another important variable, that is the limit variable. You can see that it is the maximum value that any variable can reach during the inspiration process. Remember that this value is sustained during inspiration, but it never ends with inspiration. It does not never, that limit variable can never become a cycling variable. It is the maximum value that the variable can achieve during inspiration. So if you set control variable as volume, in the ventilator you can have settings of like tidal volume 500 ml, respiratory rate 20 per minute, and IE ratio of 1:2. You will get a breath delivery. So the most conspicuous thing which you'll get in the breath delivery is that you can see here all the volume is is the same. In a when the control variable is volume, the volume delivered and the shape of the delivery is everything is the same. The flow is also the same. This is called a square flow. Now we can also have decelerating flow when you use a volume control ventilation, but mostly it is the square flow. But what is important here is the pressure is ascending, and when it reaches a peak, and it keeps varying throughout the ventilation depending upon the compliance and resistance characteristics of the patient. So here the the control variable is volume, and the variable which is keeping on changing is the pressure. In contrast, if you use the control variable to the pressure, so I suppose I set a peak inspiratory pressure of 20 centimeters of water with a respiratory rate of 20 and a PEEP of 5 centimeter water. You can see that the pressure remains a constant one throughout the respiratory cycle. I have set the pressure at 20, the pressure remains constant at 20, whereas the tidal volume keeps on changing. What you should note here is the flow is at a decelerating ramp flow. That is, once the gas delivery starts, it achieves a peak, then slowly decelerates. That is, the flow comes down as the lung starts filling with pressure. This is similar to a spontaneous respiration, where if you take a spontaneous breath, the pressure pattern is sinusoidal, that is, it rises up and goes down, whereas the flow is always in a decelerating pattern. That is why whenever you have higher modes, pressure control variable, either a pressure control or support is used because it is more physiological. It gives more patient comfort during ventilation. Coming next part, we have ventilator mode nomenclature. That is because there are it's a rapid proliferation of the modes, and all these names keep confusing you. We have a trinominal way of classifying a mode. That is, the first word should talk about the breath variable or the control variable. Second one should talk about the breath sequence. Third about the targeting scheme. So we have already seen what the ventilator breath control variable is. It is either the volume or pressure control. Let us see about the breath sequence. The breath sequence can be either continuous mandatory when the patient has no effort at all, and controlled, and once the patient starts to have some effort, it is assisted modes. The intermittent mandatory modes where the demand valve opens during the in between breaths, and patient is allowed to take some free breath when he is recovering better. So the patient's part is little bit more. So he You give him some intermittent mandatory breaths, and in between he is allowed to take spontaneous breath. Either it is in the normal pressure or it's a pressure supported one. And then once he is fully recovered, he just needs some pressure support. You have continuous spontaneous modes. Coming to the targeting schemes, there are two types. One is the manual targeting scheme where you set, and that is the ventilator obeys your command. Manual targeting schemes. The other is called the closed loop system where you set something, the ventilator looks at the signals obtained from the patient and then changes certain variables. So coming to manual targeting scheme, the basic one is called the set point. It is an open system where the ventilator responds to clinician settings only. Like if you set a volume control ventilation, like how I showed in an example, the tidal volume is 500, the respirator is 12. It means that it is the same. All the breaths will have 500 ml. So that is a set point ventilation. The second type is called the dual control ventilation, where the ventilator can switch between volume and pressure control. See, we have some pros and cons of volume and pressure control, which I'll be talking later. So if you want to get the best out of both volume and the pressure control, you can go for dual control modes. Dual control, there are various types. Within a breath, examples are volume control when you have a Pmax set in like in a Draeger ventilator, VAPS, that is volume assured pressure support. Okay, on the other name is called pressure augmentation. In this VAPS and pressure augmentation, what happens is the dual control is within a breath. That is, the breath starts either with the pressure control and ends as a volume control, or starts as a volume control or ends the pressure control. So within a breath, it can alternate. Breath to breath alternation, if it is time cycle, that is the patient, whenever I tell the word time cycle, it means the patient has continuous mandatory or continuous intermittent or intermittent mandatory. There must be mandatory breath. Only then it is time cycled. So pressure control time cycle. The example is PRVC, that is pressure regulated volume control. Whenever it is flow cycle, it's volume support, and both either time or flow, it means adaptive support ventilation. Coming to closed loop targeting schemes, the first is called the adaptive schema, where the ventilator adjusts the set point to achieve another set point set by you. The examples are PRVC and MMV. See here, it is not the volume or pressure you set. It is another variable like a minute ventilation. So the ventilator adapts its tidal volume and its respiratory rate to achieve a minute ventilation. So what happens is it is just not the pressure or the volume. Some other extra variable will be helping you to achieve the targets. The other next type is called a servo, where the feedback from the patient amplify the output. So it is called a positive feedback. The examples are proportional assist ventilation, automated tube compensation, and neurally adjusted ventilator control. Now, the difference between adaptive and servo is that servo is a positive feedback. See, suppose it gets an information, it will amplify the controller to give a bigger output. Whereas in adaptive modes, if you set a if you set a minute ventilation as target, the ventilator will keep on trying to minimize the difference between the set and the achieved one. So that is also called negative feedback. But it is not correct to talk adaptive one as a negative feedback. In optimal, rather than setting a minute ventilation, the ventilator will go to set targets on overall performance. The best example is work of breathing, and it will achieve it by using mathematical models, just not a feedback loop. It will feed it through a mathematical model, improve the output, and it will ventilate it much more better. The best example is adaptive support ventilation, which targets the work of breathing. In intelligent modes, the ventilator uses artificial intelligence and executes a rule-based algorithm to ventilate or wean the patient. In the end, I'll tell you one new name, which is interesting. And the only intelligent system which is there known as the Smartcare pressure support system. Once you start to wean, you put the patient on Smartcare. It will use artificial intelligence to wean the patient out of ventilation. It will tell you when to extubate also. So there is another thing called IntelliVent, which is an extension mode of the adaptive support ventilation. That also will help you to wean very nicely. But the exact intelligent mode is SmartCare PS system. Now coming to classification of advanced modes. I already told you I am going to classify it as extensions of the basic modes. So I have controlled, intermittent, support modes and recruitment mode. Though recruitment is not a specific mode, putting some modes into that box will help you understand them better. In conventional mode, we have assist control volume or pressure control ventilation. Then extension of that is pressure regulated volume control. So you have the benefits of both pressure control ventilation and volume control ventilation through pressure regulated volume control. There are lots of synonyms to it. The various companies do the same thing and give different names. One is the auto flow, adaptive pressure ventilation, volume control plus. All these are the same names and are different names for the same type of function. In intermittent mandatory ventilation, we have SAME mode as the conventional mode. There are few modes which have called binary modes. Like if you can add SAME with the pressure support, that pressure support will help the patient during spontaneous ventilation. You can add the SAME could be either pressure or volume. Now what they did was they thought, okay, we'll add dual to the SAME and they made it PRVC SAME. And to achieve an adaptive ventilation in SAME, they have added minute ventilation into it, which responds with the rate. Coming to support modes, the one important mode which is controlled intermittence and all support is adaptive support ventilation. I deal with it along with control ventilation. Coming to support modes, we have pressure support and the advanced modes which are based on pressure support are mandatory minute ventilation, which is pressure based, volume support, uh, VAPS ventilation, volume assured pressure support, proportional assist ventilation, Smartcare PS, which I'll be dealing because all advanced modes are pressure based, either pressure controlled or pressure support based. We have a lot of modes in the support category, and one mode which is using binary, that is, it uses pressure control ventilation when the patient is totally not having any ventilatory effort, and it will switch over to volume support if the patient has adequate efforts. That is called an auto mode. There should be, you should note the difference between auto flow and auto mode. Auto mode is a binary of PRVC and volume support, whereas auto flow is another synonym for PRVC alone. Coming to recruitment, CPAP is a classic example, and variations in CPAP like bilevel, biphasic, dual level, all the that are same. And another type of ventilation is airway pressure release ventilation. So we have seen there are a lot of ventilator advanced modes, but they will fit into each one of the basic mode category. So in conventional mode, it will be there will be a mode. The advanced mode will be an extension of it. Coming to the pressure regulated volume control. So we have already seen that it has got a lot of synonyms. It is actually a misnomer. We tell it is pressure regulated volume control, but it is actually pressure control with volume guarantee. That is the correct nomenclature of that. It is a adaptive dual control closed loop ventilation, as I already told you. It adjusts the inspiratory pressure over several breaths to maintain a set target volume. So basically, it is pressure control with volume guarantee. You set here, you can only set the volume, and with that, it will adjust the pressure, and the volume delivery will be more like a pressure control ventilation. The descriptive points are, it is either time or sometimes patient triggered. It is a volume targeted mode and it is time cycled. It is very useful in sedated paralyzed patients who are recovering from that sedation and paralysis and whose lung compliance and resistance keeps changing. There, you can assure that some good tidal volume is delivered with a pressure type of delivery, pressure control type of delivery. So what you will set is, you'll have to input the weight. Then you will have to set a tidal volume. See, in the pressure control mode, you will only set the inspirated pressure. In PRVC, it is always the tidal volume that is set, and you will also set a pressure limit. Once you set this and start ventilation, what will happen is the ventilator will deliver a volume controlled test breath. So it is a volume controlled test breath, approximately at 10 ml per kg with an inspiratory pause at 10%. So why this inspiratory process there is there? It is there means it has to measure the P peak and P flat. Once it gets the two values, that P peak and P flat, what happens is it will start delivering a pressure control breath. So this is the first volume control breath. It has delivered. It has calculated the P peak and the P flat. Once it has done so, it will convert the total ventilation into pressure control mode, and it will start to give the delivery with the pressure as the plateau pressure. See, you have already calculated the plateau pressure here. It will start delivering the breath with the peak inspired pressure, the plateau pressure from the volume control breath, and it will keep aiming for the tidal volume, that is the 400 ml you have set. It will try to achieve that with the least amount of pressure. So this is the flow diagram. It initially gives a test breath. You measure the tidal volume. Now what it does is it will start to give the inspiratory pressure. Compare the set volume, set tidal volume. If it is less, it will start to slowly increase the inspiratory pressure. As the ventilation goes on, the inspiratory pressure will slowly rise from the P plateau levels. Peak inspiratory pressure will start rising and will try to target that tidal volume in decelerating flow. So what happens if the lung is not compliant? So you have already set a maximum inspiratory pressure limit. So here that cannot be crossed. What happens is it will slowly increase the tidal volume. Once it is the pressure achieved with that tidal volume is 3 to 5 centimeter less than the set pressure limit, it will terminate the breath and will give an alarm. And only that amount of tidal volume can be achieved in that patient. The advantages are it has got a physiological decelerating flow. It has got more patient comfort. So there is no barotrauma, but still you get a guaranteed tidal volume and minute ventilation, more safety, especially in ARDS. Many trials have been done with PRVC and they are approved. It is very safe when low tidal volumes are set with an guaranteed minute ventilation. It is very useful when compliance and resistance are continuously changing, as I already told you. The disadvantage is it cannot be used in a fully awake or spontaneous breathing patient. So when the patient is recovering, you can switch over to PRVC SAME plus pressure support mode. And if the patient has a high flow demand, it can lead to increased work of breathing over a period of time. I emphasize this point as I go on in this lecture. And you cannot use this mode as a primary mode when there is an obstructed airway or an airway leak. So when the patient has a high vigorous drive, the patient is starting to recover and is having a vigorous drive or high ventilator demand, what will happen is because of his effort, he will initially achieve the tidal volume you have set. Remember, in PRVC, I already told you tidal volume is set. So he will somehow achieve the tidal volume. The ventilator will think he is recovering well and he will start to reduce the pressure. As the pressure reduces over a period of time, he will have less pressure support or less pressure assistance to take that tidal volume. He will become fatigued. So this is one disadvantage of mode. This is a pressure asynchrony that can happen in PRVC. So as the patient starts recovering, when the patient needs a lot of pressure support when he recovers and to get out of the ventilator fast, the pressure support will start to reduce. And because initially he was getting a good tidal volume. Here you can see that there are few modes and comparison of the airway pressure in comparison to the patient effort. So as the patient starts to take effort, if the patient is in a pressure support or a pressure control mode, the airway pressure remains the same. It does not change. And in a volume control ventilation, as the patient starts to recover and have a better effort, the airway pressure starts reducing. That is the characteristic of volume control ventilation. But see here, in PRVC, as the patient's effort starts reducing, the increasing, the pressure support becomes less and less. Then coming to the next mode of ventilation, that is adaptive support ventilation. It is also called as pressure control with minimum volume guarantee. It is a servo control mode with optimal targeting scheme. I already told you, adaptive means it is a respiratory parameter, but in optimal, you have a higher value that is calculated with many parameters. So here it provides a specific minute ventilation. So with it is also a minute ventilation, targeted ventilation, and it also ensures effective alveolar ventilation with the lowest work of breathing. Here the optimum word is for the lowest work of breathing. It can function from fully controlled, that when the patient is not having no effort at all, to a fully spontaneous mode. And until event, as I already told you, you can set PEEP, FiO to respirate it from other variables obtained from the other monitors like SpO2, BP, N-tail carbon dioxide. With that, it can set PEEP, FiO2 and respiratory rate. So it becomes a totally automatic mode. And even a spontaneous breathing trial can be performed, and the ventilator will tell you when to extubate. What you will input is, once the patient is intubated and connected to ASV mode, the patient's age and height will be input. With that input, it will calculate the minute ventilation, that is 100 ml per kg per minute. It will calculate the minute ventilation for that patient. And then it will also, with the dead space, it will calculate the alveolar minute ventilation. It will reduce that 2.2 ml per kg, it will reduce that, it will say that, so this amount of dead space is there, his alveolar minute ventilation is going to be the rest of that. So with that, what you will have to set is, you have to set the percentage of minute ventilation what you want to achieve. Suppose you have 100 ml per kg per minute and you want only 70% assistance, you can set 70%. You want 200% assistance because the patient is in a metabolic acidosis or sepsis or fever, you can set 200%. For with a wide range, you will have to set what percentage of minute ventilation you want to get supported. So you are entering the patient age, height, it will calculate some parameters, then you will have to calculate what percentage of minute ventilation you want to get supported. Now, once you enter this, it will give a volume control test breath. And once it gives that, it is going to calculate the dynamic compliance and the expiratory time constant. It's a little bit different from all other modes. It will calculate the compliance and the time constant. With this, what it will do is, it will take three parameters. First is, it will calculate the inspiratory time. Inspiratory time, it will be no less than one time constant. Expiratory time will be at least three time constant. That is why I told you, if you go to the previous videos, you will understand this better. And with the dynamic compliance, it will calculate what pressure it should give to ventilate this patient based on this formula. F is equal to 1 plus 2 into time constant into the dead space minus 1 by the time constant. With this formula, it is going to start the ventilation now. What happens is, once it starts the ventilation, it will change the ventilation parameters depending upon the work of breathing, which is derived from a OTC equation. This OTC equation will give you the least amount of work of breathing which is obtained with the respiratory rate. So it'll calculate a mathematical model. It will adjust the rate and the pressure to that mathematical model, and it will give the best ventilation where the work of breathing is very low. And it will also has a square. This rate and pressure cannot go out of. These are called runaway parameters. It will fence that rate and pressure within the uh, uh, physiological values. It will not allow it to go away or run away parameters. Coming to the next mode, that is the intermittent mandatory ventilation. So here you have one advanced mode, that is mandatory minute ventilation in SAMV. Suppose I set a volume SAMV plus PS with tidal volume of 400 ml and a mandatory rate of 8 per minute, and I set a alarm rate or upper limit of minute ventilation to be 5.6 liters per minute. Now I have set this all in this ventilator. Now what happens is, the mandatory minute ventilation, suppose the patient does not have any breath on his own, what happens? It will give 8 breaths with 400 ml, that is, his minute ventilation will only be 3.2 liters per minute. Now he is going to have spontaneous breaths. So I support that spontaneous breaths with a pressure of 12 centimeters of water. Now in the ventilator I'm going to see he has 16 breaths. So it means that apart from the 8 mandatory breaths, is also is extra taken 8 more breaths, but his tidal volume is low. It's only 200 ml per minute. So the total minute ventilation is 400 plus 8, that is the mandatory minute ventilation, plus 8 into 200, that is his spontaneous breath. So totally only 4.8 liters per minute ventilation has occurred. Now I want to raise it to 5.6 liters per minute. So what happens is the ventilator will start increasing the mandatory rate. So now we can see that it has increased the mandatory rate from 8 to 10 and it has achieved 5.6 liters per minute. This is the mandatory minute ventilation where rate is increased and the minute ventilation is achieved. Coming to pressure support modes now, the control modes are over. The intermittent mandatory modes are over. Coming to spontaneous pressure support modes where you have the maximum number of advanced modes in this. So a pressure support is for the first is here spontaneous breath. I'm showing a spontaneous breath here where there's a negative deflection during inspiration and positive deflection during exhalation. And as I already told you, the flow is in a decelerating pattern. I am achieved a volume here. A supported breath is where spontaneous breath is supported with some amount of pressure that is needed to overcome the tube resistance or the work of breathing is reduced. So here also it is a decelerating flow pattern and see you have achieved little bit more tidal volume than a spontaneous ventilation. So in pressure support, there are parameter the descriptive modes are patient triggered, pressure limited, and it's a flow cycle. Because it is a spontaneous mode, it's always flow cycle. There are a few parameters which are added to spice up the pressure support. The first is called the rise time or the slope. So here in this you can see that immediately when the patient has triggered, the flow rate has become maximum. It has just pushed air into him. Now, if you want to keep the patient a little bit more comfortable, it gives him some time to adapt and take the volume in. You can set a rise time. So, see here in this you can see that the after the uh, trigger, it has taken some time to reach the peak flow. That can be set either as time. Usually we set 0.1 to 0.3 seconds. In the total inspiratory time of 1 second, 0.1 second will be taken to raise the flow to the peak. Or you can set a slope like 10 to 20% of the total inspiratory time. So inspiratory time is 1 second. 0.2 seconds will be spent in increasing the flow to the peak. So these all methods will give comfort to the patient. You can see in this example, see here the inspiratory time is only 0.8 second in the A diagram. The inspiratory flows overwhelm the patient with the sudden increase in in the flow. So you can see a peak in the it's a type of asynchrony where there's a very high flow. So what the B flow B in B what they're doing is they're setting a rise time or a slope. Slowly they're giving a time for the inspiratory flow to increase. Now the flow rate has decreased and the patient has become more comfortable. But what happens is if you increase it more, the patient will start to vigorously take in breath and the total flow itself will decrease. So you have to sit near the patient and set the rise time where the patient has the maximum comfort and the good delivery. Another parameter is called the exhalation sensitivity or where the flow cycling has to take place. See, suppose you support a breath with say 20 centimeter pressure and keeps on giving. When the patient wants to exhale, it has to stop giving. So for that, we have something called expiratory sensitivity. So once it starts giving and the flow goes up and starts decelerating, once the flow becomes 25% of the peak value, the ventilator will go into exhalation or it will cycle. That will give more comfort to the patient. Suppose the patient's neural exhalation time is less than that, you can cycle the flow at 40%. You can increase the percentage, the flow will cycle from inspiration to expiration earlier and earlier. So these two small parameters have been added to pressure support to ensure make more patient comfort and safety. So what is the advantage of using pressure support? It will increase the tidal volume, it will reduce the frequency of work of breathing, thereby it will enhance the weaning process. But there are still some problems with it. See, if the lung mechanics are not good, what will happen is only the same pressure what you have set will be given, and the tidal volume, like the same problem with pressure control ventilation, you suppose you set 15 centimeters of water in a poorly compliant lung. That 15 centimeters of water pressure support will be given, but the tidal volume may not be achieved. That is the problem with pressure support. So to overcome that, like how we have a mandatory ventilation in IMV, we have MMV in PS also. So suppose they have set a pressure support. I have set a support of 12 centimeter of water and I have targeted a minute ventilation of 5.6 liters per minute. I'm getting a total frequency of 16. That is, he is in spontaneous. So all his breaths are in spontaneous mode. He is taking 16 breaths, but all his even with 12 centimeters of water, his tidal volume is only 200. Now what will happen is his total ventilation again will become only 3.2 liters. To achieve extra 2.4, that is to get a minute ventilation to 5.6, the ventilator will start increasing the pressure support slowly. You have set 12, but the ventilator will start slowly increasing the pressure support so that your tidal volume will achieve the minute ventilation. That is, for each breath, it will try to get 150 ml extra by increasing the pressure support. So, MMB in PSS, it will increase the pressure support to achieve a minute ventilation that you have set. So, the next advanced mode is called the volume support. So, it is an adaptive mode where the pressure support increases to achieve a preset volume. So, there in the previous mode, we wanted the target was a minute ventilation. Here, it's a tidal volume. So you set a tidal, like how in PRVC you set a tidal volume in a pressure control. Here in pressure support you set a tidal volume. The descriptive parameters, it's a pressure triggered, volume limited, and because it is a spontaneous mode, it's a flow cycle ventilation. Here you can see that I am not setting the pressure support, but I'm setting a specific tidal volume, which I would like to reach when the patient is spontaneous. So here you can see that the first, second, third breath, the volume is slowly rising up, and in the third breath, it has reached a good pressure with a good set for that set tidal volume, and it will maintain the same pressure throughout for delivering that tidal volume I have set. If the patient is starting to improve or he is taking good effort more than this, it will start to reduce the pressure support and achieve the same tidal volume. So that is how the volume support works. So initially, it will give some breaths. It will see whether if I am able to achieve the tidal volume which I have been set in start of ventilation. If it is not set, the next breath will get little bit more pressure. Next breath will get a little bit more extra pressure until the tidal volume which I have set is achieved. Once it is achieved, it will stay there, and once the patient starts improving, it will reduce the pressure support. So this is good effort area. The problem is if you set low tidal volume, if the patient might need 500 ml. If you set low tidal volume, he will start to fight with the ventilator and increase his work of breathing. Or if you set higher tidal volume, it again delay weaning and produce auto peak. But uh, but in general, when a patient is recovering from general anesthesia, it's an excellent weaning mode because it's got higher safety and comfort. Now see, we have seen two modes, PRVC, which is time triggered, volume targeted, and time cycled. In a similar way, it looks almost the same, but it's patient triggered, volume targeted, and flow cycled. But now if you combine these two modes, you will get a super mode called auto mode. It's not auto flow, it's auto mode. It is a combination of PRVC and volume support. If there's no effort from the patient at all, the ventilator functions like a PRVC. It will give a volume test breath. It will determine the plateau pressure and it will use that plateau pressure as the peak inspirator pressure and it will give pressure control breaths. But if the patient has two or more inspiratory efforts, immediately it will change to volume support and it will start to achieve that same tidal volume with optimal pressure. And once it starts recovering, it will reduce the pressure. So this auto mode can be used from control to support modes as a one mode. Next is VAPS or volume measured pressure support. This is a dual mode which uses within a breath. It has both controls within a breath. It will function like a pressure support when the patient has a good spontaneous efforts and good tidal volume. If the patient does not have good tidal volume, it will go into a volume controlled or a volume assisted ventilation. Let us see how. It is a preset pressure support mode with minimal tidal volume set. For a given PS, if the target tidal volume is achieved, the volume control mode will not be activated. But suppose if the patient has a very poor effort, the sensor will look at the end of inspiration. If even just before the inspiration is going to get finished, it will see whether the set tidal volume is achieved or not. If it is not achieved, remember it's a pressure support mode. It will convert to volume control mode. It will finish giving that volume in that same breath itself and will cycle. So see here, the ventilation started, it is about to end, the set tidal volume is not achieved. So immediately it has changed its shape to another mode of ventilation. So you can see here, in this is the volume control ventilation. The pressure is rising to a peak and then coming down. And the tidal volume is achieved here, it is coming down. So within a breath, if there is a dual control, it is always volume assured pressure support. Nowadays, this mode is not in uh, uh, big use in the current clinical practice. The next important mode is the proportional assist ventilation. It is a servo control adaptive mode which is used to achieve an adequate tidal volume. Here it is patient triggered, variable targeted. It could be any target. It's variable targeted. It is either flow or volume cycle because it's a spontaneous mode. What you set here is you set the patient's weight, percentage of assistance, and you set the runaway limits. Runaway limits means you set that tidal volume should not be more than 20. Your minute ventilation should not be more than 8. Your respiratory rate should not be more than 20. Something like this. If you set those limits, it's called runaway limits. Because it's a fully automated mode, you should see to that the mathematical calculations don't drive these patients into very high rates of high minute ventilation. So in similar way to other modes, here also a test breath is delivered. And in adaptive support ventilation, the elastance and airflow resistance is calculated, and it will ask you what amount of assistance you need to support. And once you set that, the pressure support is delivered in proportion to the initial inspiratory flow. As I told you, these are all adaptive and more than that optimal modes. So adaptive mode means it is always as a servo mode, it will increase the feedback. So a small effort will have a amplified output. It's like a steering wheel. You slightly turn the car, it will move to a longer radius. So in previous days, you will have to keep turning the steering wheel to achieve a turn. Now it is a slight turn, you will have a big, proportionally a proper turning. So it is like that. So if I suppose if I deliver, and if the machine delivers a breath, it finds the elastance to be 40 centimeters of water. To deliver 1 liter of gas, it will need 32 centimeters of water. That is how it goes. PAV varies from each breath to breath to match the patient demands. So this pressure support, the pressure high will keep on varying in response to the initial inspirated demand the patient has. If he has more demand, the pressure support also will increase. So, if you remember this picture, we already showed you that in pressure support and pressure control, the airway pressure remains the same with changing patient's effort. And in PRVC, ACV, and IMB, the airway pressure keeps decreasing and the patient develops good effort. In proportional assist ventilation, the pressure support will increase in response to the patient's effort. If the patient's effort is increasing, it will amplify that signal and will give more pressure support to the patient. Let us see by an example. Say I have set enteral carbon dioxide, airway pressure and volume. Now what I'm going to do is for a spontaneously breathing patient who has pressure support, I'm going to in various modes, I'm going to give carbon dioxide to him or make him hypercapnic and see the response. See in volume assist control, suppose this patient is on a ventilator with volume assist control, he is spontaneously breathing and his carbon dioxide level goes up. What will happen is he will become tachypnic, but his airway pressure will become low because he has more inspirated demand and it's not met by the ventilator. His airway pressure will go down and become tachypnic. In a pressure support, the same pressure will remain. He will become tachypnic, but the volume delivered become a little bit better. See the difference in proportional assist because of his hypercapnia. he is trying to hyperventilate, but that is sensed by this PAV and it is increasing the pressure support, and in response the volume is also increasing. In this mode, the patient will never get tired. In these two modes, if the patient is hypercapnic or is sepsis or he is having a high demand for oxygen and is hypercapnic, immediately he for some time he will have good minute ventilation, then he will become fatigued. That is the advantage of PAV. Coming to the last mode, that is Smartcare PS on pressure support. It is an intelligent pressure support system that helps in weaning and extubation. It uses an AI system called Neo Ganesh. It's a different name which when I was reading. It uses that algorithm to support the pressure. So it does that in three steps. First is if the patient is in a spontaneous respiration, and you connect him to Smartcare PS, it will set the tidal volume, respiratory rate, ventilation, depending upon other variables in the zone of respiratory comfort. That AI will tell you what the respiratory comfort is. It will set some tidal volume, it will set some respiratory rate, some pressure support, and it will ventilate that patient. And slowly it will reduce the inspiratory pressure, making sure that patient remains in the safety zone. Suppose it reduces inspiratory pressure, it reduces the respiratory rate support, but the patient should remain in the safe zone. If he is away from the safe zone, he immediately step back the support. That is how it works. And when once it reduces the lowest inspiratory pressure support, it will automatically start a spontaneous breathing trial. And once the patient passes an SBT, it will indicate with an alarm that the patient is ready for extubation. You can separate the patient from the ventilator. That is smart care. Next, coming to neural adjusted ventilator assist. See, once how the physiology is, the dorsal respiratory group gives in firing to the phrenic nerve, and that goes to external intercostals and diaphragm. And diaphragm immediately takes that electrical signal and it contracts. It alters the chest wall mechanics. We have talked about the trans-respiratory gradients that will alter the mechanics, and it will make the air flow from the atmosphere into the alveoli and will create an airway pressure. Now in ventilator, if you do the same, it takes a long time. The airway pressure has to change, and now it has to trigger the ventilator to assist or support. Now the pressure assist or support will have to the brain's activity has started a long time earlier. The actual assist takes a little bit later. So what happens is the patient will have asynchrony, and because of the time delay, and maybe his support is also not proportional. So to overcome all these problems, in NAVA has come into existence. So you can see here what they do is they send a electrical sensor in into the esophagus and place it near the diaphragm, where it will measure the voltage in the diaphragm. That's called EAD, or diaphragmatic electrical activity in the diaphragm. And once that is sensed, it will trigger the patient into inspiration. The pressure assisted or supported breath starts immediately on detection of the electrical activity, thereby reducing the time delay, and this will reduce the asynchrony in the patient. And it will also give a breath which is in proportion to the amount of electrical activity in the diaphragm. So you can set a NAVA level, like if I want a airway pressure to be adequate, and the diaphragm electrical activity is at 8 microvolt, NAVA level is at 2, it will support with 16 millimeters of mercury. That is how if in proportion to the diaphragmatic electrical activity, the airway pressure will start developing. Like in PAV, how you had an inspiratory pressure or flow is sensed, and the pressure support keeps on increasing. Then set NAVA level, we look at the EAD, and then it will give the airway pressure. And cycling, here you can see that it will occur when the diaphragm electrical activity comes down to 70% of peak value. Like in pressure support, how you saw that when the flow reduces to 25% the initial value, it will cycle. In a similar way, when it comes down to 30%, it will cycle. So NAVA is a very advanced mode. It is more physiological, it is more synchronous, more comfortable, and it gives good tidal volume and ventilation support. The only thing is the cost and the availability factor, which is limiting in regular clinical use. Servo I, the Macwood in its ventilator has incorporated NAVA so that it gives more comfort. Yes, coming to spontaneous breathing modes. This is spontaneous ventilation. As I already told you, you have negative inspirated deflection and a positive expirated deflection. Now, I am going to a CPAP mode, where I set a higher airway pressure throughout the respiratory cycle, and patient starts taking spontaneous breath on that CPAP level. So what is the advantage is the alveoli is always kept little bit open. The FRC increases, the alveoli is always kept in a little bit more open state, and the inspiration takes above that the new FRC. That is how CPAP works. This is spontaneous plus CPAP. Now what I do is I give little pressure support in that spontaneous mode. So his tidal volume is going to get little bit better. The thing is, when I'm in CPAP, pressure uh, uh, solenoid valve gives pressurizes the entire circuit. Now, when I want to breathe spontaneously, the demand, inspirated demand and expirated demand valves keep themselves open. And even during any type of ventilation which is based on the spontaneous breathing modes, the demand, the inspiratory and expiratory valves keep moving, and you can take as much of spontaneous breath, which would be either fully spontaneous or pressure supported spontaneous breath in that breath, ventilatory mode itself. Now I'm talking about bilevel. In bilevel, what you do is you set high pressure for a particular amount of time, low pressure for a particular amount of time. In CPAP, what you had is same pressure for the throughout the respiratory cycle you had. Now you go a little bit extra, set some pressure for some time, set some low pressure for some time. So here it is. You can see here there is high pressure for some time, low pressure for some time. The IE ratio is maintained like how one is to, like a physiological way. If you maintain the IE ratio and allow the patient to take a spontaneous breath, which could be spontaneous or pressure supported, it's called bilevel or BiPAP or duo level, whatever the name is. You have two levels of pressure support, high, low, and you are maintaining the physiological IE ratios. It's called bilevel. Suppose I don't maintain the physiological IE ratio. I want to have an inverse ratio, that is a long inspired time with a short expired time, is called APRV. That is the only difference. APRV is a bilevel ventilation where the inverse ratio of ventilation has been applied, and the patient can spontaneously breathe either spontaneously or pressure supportedly throughout the bilevel and APRV. So this is a pressure, flow, and a volume diagram for APRV. You can, I'll tell you one where it is very useful. Now, this is the pressure volume loop. The lower part is called the lower inflection point. The upper where the valve will completely collapse. And here, if you deliver volume, only the pressure will increase. And once the alveoli becomes open, the pressure will for a given pressure, the volume will fill exponentially. And once the upper inflection point, that is the point of over distension is reached, any amount of volume will only increase the pressure. So in a patient with ARDS, if the patient is fully paralyzed, I will only use tidal volume, lung protection ventilation with the volume control ventilation. So here, when the patient becomes spontaneous, you can use this to keep the valvula recruited. So I'll choose this APRV. The airway pressure is kept high throughout the respiratory cycle so that the alveoli remains open and it gives better oxygenation. And by using APRV, you will always stay in the safe zone. That is the place of the maximum compliance. And you also know that ventilator-induced lung injury happens because constant deflation and high inflation. So, because the alveolar duct junction will develop cracks when the alveoli keeps on getting fully deflated and fully inflated. So, if you use APRV, it will be in a semi-open state and will protect against biotrauma or VLA. That is the advantage of using APRV. Coming to high frequency ventilation, there are three types. high frequency jet ventilation, high frequency oscillatory ventilation, and high frequency percussive ventilation. High frequency jet ventilation is probably used when you have airway surgeries. You use a jet ventilator, which uses a Venturi principle. High frequency oscillatory ventilation is used in pediatrics. Suppose you can use 500 breaths per minute in low tidal volume, it will benefit the neonate. The same thing when it is used with the BiPAP or APRV, it is called high frequency percussive ventilation. Here, see here, it's a low tidal volume, high rate somewhere around 500. There is an IPAP here. There's together with IPAP, I have added high frequency. Together with the EPAP, I have added high frequency. It's called high frequency percussive ventilation. I don't want to go into that all the details of high frequency ventilation for want of time. So to summarize, conventional modes are volume control and pressure control. The dual mode, which is an advance of AC, VC and PC, is pressure regulated volume control. It has got synonyms out of low adaptive pressure ventilation and volume control plus. Adaptive support ventilation is a type of control ventilation, but it can travel right through intermittent mandatory and continuously spontaneous modes also. It is based on achieving a minute ventilation, and it is an adaptive mode and an optimal mode because it uses uh, it uses work of breathing to target the respiratory rate and tidal volume. In support modes, that is pressure support modes, the higher modes are uh, volume support, volume assured pressure support, proportional assist ventilation, and Smartcare. In recruitment modes, that is the better modes than CPAP are not better, that the advanced modes based on CPAP are bilevel modes and APRV. The take home message is that conventional modes, they're very safe, but the only thing is you need more clinician interaction. You have to sit near the ventilator and adjust the ventilator as the patient recovers. And sometimes it might be less comfort for the patient because you don't have any freedom during ventilation. But advanced modes, though they are extensions of conventional modes, are they really safe? We don't know. Sometimes there are specific entities like closed loop asynchrony, runaway errors that can occur because the machine is fully automatic now. It's not under the control that can occur. So is it really safe? You have to be near it. Is it really comfortable? That is also you don't know because it's fully automatic. But definitely with help of mathematical models and AI, it has become a little bit more comfortable. Does it really need less clinician nearby or has interaction? That is also questionable. So you will have to use advanced modes with lot of care. So you have to acquire knowledge. You have to have good operating skill. You have to work under a mentor. You have to understand that mode and use it with diligence whenever it's needed. That will to give you the maximum output. Thank you for your patience listening.